Hi, I'm Ben-Yaakov. This presentation is entitled Overvoltage Protection of PWM Half Bridge, Misconceptions and Facts. I'm showing here a half bridge including two transistors, and then I'm showing also the leakage inductances. Of course, there are some leakage inductances within the package which I'm not considering here, and also showing the output capacitance of the transistor C sub OSS. Typically, we are going to have a bank of capacitors here, and then here's the input voltage. Now, this half bridge is normally the building block of many types of PWM converters, including a synchronous back, DC to DC half bridge, full bridge, and then a DC to DC phase shifted PWM converter. And of course, it would be the one leg of a DC to AC inverter for two-phase or three-phase inverter. We're in particular interested in this presentation in the turn-off instant. We have now the transistor showing here conducting. We have the current flowing through the transistor out to the inductor. Current is normally be rising. And here we have this instant of turn off. Transistor is turned off, the current is going down within the transistor, and the VDS, the voltage across it, will start rising. At this point, the current will actually pass through the capacitor, and between the inductor and capacitor, we have now a resonant circuit. And depending on the size of the inductor, capacitor, and the initial condition of this situation, here we have it. We have the inductor, initial current. This is the current just before the turn off. This is the output capacitance. Then here we have a resonant circuit. Consequently, we're going to have here a sinusoidal waveform, sort of, and a voltage which is higher, of course, than the bus voltage. And this is our concern here, that we don't want this to be too high because it can actually damage the transistor. Later on, of course, the lower transistor will be turning on and the current will be flowing through this transistor. And this will be this part here. Now, in order to reduce the maximum voltage across the transistor, we can use the snubber, which is the subject matter of this presentation. And in general, a snubber is basically a capacitor which is put in parallel to the transistor. Now, obviously, you can't do it in this simple way which showing here. This is just explaining the behavior of the circuit at this instant. You do have to do something else, add some more circuitry, because if this is kept as it is, then the energy dumped into the capacitor, or the voltage, or the energy stored in it will be moved or dumped into the transistor when it is turned on. And this, of course, will be increase the losses. So you do have to do something else. I'll talk about it in a few minutes. But for the purpose of explaining the help that this capacitor is actually providing in lowering the voltage, we have this basic circuit here, and what happens is that this same energy which goes into this capacitor now is lowering the peak, and we have a lower voltage. So this is the basic idea of an RCD snubber. I don't show the R or D as yet, just the capacitive component which is responsible for lowering the peak voltage. Now, the actual implementation of such an RCD could be of this nature. This is the very basic or classical RCD snubber. What we see here is a diode and a capacitor, so the current will be passing this way at turn off, and here it is actually showing the same thing. The transistor is off, the current is passing here to the snubber. But in this case, this is a discharging RCD snubber. So when the transistor is on, then the current is flowing through the resistor into the transistor, and actually dissipating the energy or the power here by this resistor. So this is causing, of course, losses, because each cycle you charge and discharge the capacitor. So these are typically of high loss type RCD, although they'll do the job in terms of clamping. Now, another advantage of this snubber is that it is also slowing down the VDT during the turn off, because as the current is passing through the capacitor, which is now discharged at turn off, it'll start rising depending on the size of this capacitor. The voltage will, the rate of rise of the voltage will be slowed down by this capacitor. So this helps here. But we are not concerned with this issue at all. We are concerned with the overvoltage. For this purpose, this snubber is really very highly lossy, and there's a lot of power loss involved here. A better way would be to use a snubber which is charged to about the bus voltage just before the turn off. And I'm showing it schematically here, and later on we'll see how we can realize something like that. But let's assume now that this capacitor is charged to VB plus. So what will happen is that as the current is flowing, it'll be clamped by this capacitor, and then when the transistor is on due to this diode, then we are not discharging to zero this capacitor or to a lower level. Okay? In fact, we'll be discharging it into the bus voltage. We'll see it in a minute. So here, what really happens, at turn off, the voltage of the transistor is going up. This is this voltage, and this is the voltage of the snubber, the green one. This is the inductor current of the leakage inductor. So at this point, the voltage of the transistor reached the voltage of the snubber, and it is now clamped here. And as you can see, this inductor now current of the leakage inductance goes down sort of sinusoidally, because there is a resonance between this and this capacitance, but this is now a larger capacitance, so the increase in the voltage here is fairly small. So how can we keep the snubber voltage at the bus voltage? That is not to discharge it, and then however we do have to get rid of the extra energy which is dumped in at turn off. And this is done conveniently by this configuration. This is the snubber, which includes this capacitor, the diode. Here we have this path of snubbing, but then there is another resistor, the purpose of which is actually to discharge this capacitor to the bus voltage. So let's see how this thing works. Here I have this part here. So we see that at on state, the current is passing through the transistor. Then at off, we have the current through the capacitance, output capacitance of the transistor, and the current going out. Voltage of the transistor starts to rise, and then it hits the 400 volt, which is the voltage of the snubber. I'm assuming a bus of 400 volt. And then we might have some increase of the voltage depending on the size of this capacitor. We're going to talk about it quite a bit. And so this is the point at which we have some increase of the voltage. And then what is happening is that this transistor, the lower transistor, is conducting, so the current of the main inductor is going this way. And now we have a resistor which is discharging this capacitor for the extra power or energy that is stored in it back, actually, let's see it here, back to the bus, So we have this voltage now a little bit higher than the bus voltage, depending on the peak voltage. And then by connecting actually the capacitor to the bus, we are discharging it to the bus voltage. Now, we know that when we discharge a capacitor to a voltage, we are losing half of the energy, and half of the energy is actually being transferred. So half of the energy that was dumped into the capacitor is lost, and half of it is actually going back to the bus. So the question is, what is the size of the snubbing capacitor that you need? How much capacitance do you need here? Now, let's assume that we are specifying the maximum voltage that you would like to reach, okay? This delta B, which is the plus VB, is V peak. So this is the circuit that we are examining. We have the bus voltage, we have the initial condition of the leakage inductance, the I sub 0. We have the charged capacitor charged to VB, as a matter of fact. And I can represent this here, this charged capacitor, by a model which has a voltage source plus a capacitor which is actually charged to 0. There is no voltage across it. So this is a model of this charged capacitor. And as we see here, these two actually cancel each other. So I'm left with this circuit, this simple resonant network. We have an inductor, capacitor, initial condition of I sub 0, and as we know, we are going to have a sinusoidal waveform. I'm looking now at the voltage across the capacitor, and we know that it will reach I sub 0 times the characteristic impedance of the circuit, which is the square root of L sub S over C snubber. So this will be the delta B that will be added here, which is actually added to the capacitor, which is already charged to VB. So V peak is this delta B plus this height. That is VB plus delta B, which is I sub 0 times the characteristic impedance. So here we have delta B is equal to this, V peak is equal to VB plus this delta B, and just moving this to the left, and then taking the square of this expression to get L sub S and C sub N, here it is, I can express the capacitance of the snubber capacitor as I sub 0 square Ls divided by the difference here square. So this is the size of capacitance that you need for this V peak over V bus, assuming that we started with a capacitor which is charged to this V bus. As an example, let's assume that we have a 30 nanohenry leakage inductance, 20 amp, 400 volt, and we want V peak not to exceed 430 volt or to be equal to 430. So here we have I sub 0 square is this 20 square, which is 400. Then we have the leakage inductance, here it is, and the difference is 30 squared is 900, and we come up with this inductance, which is 13 nanofarad. So this is how much we need in order not to exceed the 30 volt above the bus voltage. So the question is, this energy that we have, where is it coming from, and is it really the energy of this inductance? That is, the inductance, so the leakage inductor has a initial condition of I sub 0, so therefore it has an energy of L I sub 0 square over 2. And the common wisdom and conventional intuitive feeling is that this energy now is actually moved to this capacitor. So this is the sort of the first impression you get from a circuit like that. But as it turns out, this is wrong. The amount of power or energy for each cycle that is moved into the Snubber capacitor is much, much higher than this thing. So let's see how much is it. And I'm doing here an approximate analysis just to get an intuitive feeling of what is really happening. Of course, we can solve the differential equation, get an exact result, or we can do simulation, which is the same thing, which I'm going to do later on and show the result. But in order to get the impression of what is really going on here, let's do this approximate analysis. In this analysis, I'm assuming that the increase in the voltage of the snubber is not very high. That is, the peak value is not too high as compared to the bus voltage. Okay, so this is the basic approximation that I'm using here. Secondly, I'm taking into account that the current is going down sort of sinusoidally, because as the current is flowing here, we have this resonant circuit, and whereas the voltage of the capacitor is going up sinusoidally, very little, because the capacitance is high, the current is going down sinusoidally, and I'm expressing it as I sub 0 times sinus omega t. And we're interested in this period, on this time between 90 degree of the cycle to 180 of the current cycle or current waveform. Now the total charge that is transferred to the capacitor is the integral of this current, and from 90 to 180 degree, and here it is. This is minus cosine omega t, and it comes to be I sub 0 over omega. Okay, I sub 0 over omega is the amount of charge that is moved into the capacitor. Now, if we assume that the voltage of this snubber capacitor does not change much, it's about bus voltage, then the energy is the Q times V, which is this ratio, I sub 0 over omega times VB. So this is the amount of energy which is moved from here into this capacitor. And I can express omega as 1 over square root of LC, and therefore the energy is I sub 0 VB and then square root of LC. So this is the period of the angular frequency of this circuit. Now the power is the energy times frequency, so this will be the power that actually is being moved to the snubber capacitor. This is this expression. So let's take an example. If we have again 13 nanofarad, which we found before, 20 amp, 30 nanohenry of inductance, 400 volt, and we assume a switching frequency of 100 kilohertz, we come up with a value, this is the power, of 16 watts. This is the amount of power that is moved to the capacitor. Now, during the discharge, this energy is dissipated partly by the resistor and partly it's moved to the bus. We know that when you discharge a capacitor into a voltage, you lose half of the power, that is, half of the power is dissipated in the resistor and half of it will be actually recovered. So we are losing or recovering half of this value, which is 8 watts. Now, what about the energy that was in the inductor, the leakage inductance? This should be I square, of course, and here it is I square. I'm sorry, it should be here I0 square. So we have I squared, 30 nanohenry, 10 to the minus 9 over 2. This is the frequency, and we get 0.6 watt, much lower than 16 watts that we found as a total power that is moved into the Snubber capacitor. So what's the reason for it? Well, the reason for it is, let's go back here, that when the current is flowing into the Snubber capacitor, it's actually coming off the bus. So energy is actually coming off the bus and moving. There's an energy transfer directly from the bus voltage or bus source to here. Now, this is a function of the time that it takes for this current to decay. And if the frequency will be lower, that is, it'll take more time, then the amount of power will be higher. And we can see it here. Omega here is the denominator. So the smaller the omega, that is the lower the frequency, the higher is the energy. So if the timing is such that the inductor current is decaying very fast, then of course we are going to have a lower energy. But then the voltage of the capacitor, Snubber capacitor, will be higher. So we have a catch here regarding the amount of energy moved to the Snubber and the peak voltage, and I'm going to show it later on by simulation. So here is the simulation model. I have here the bus. This is 400 volt, the leakage inductance 30 nanohenry. This is a voltage source, 0 voltage for measuring the current, parasitic resistance, diode. I've put here a capacitor because I had some convergence problems, and this sort of helped out the circuit to converge. We have a ESR sort of 20 milliohm and a Snubber capacitor, which is pre-charged to 400 volt. The initial conditions are 400 volt. Now on this side I have an ABM, which is analog behavioral model, in which I'm doing the calculation according to the approximate equation that I've developed. This is the current, this is the inductance times capacitance to the power of 0.5, the square root of it, 100 kilohertz, and 400 volt the bus voltage. So this is the power approximate by this equation. And here are some typical results. This will be for a Snubber capacitor of 11 nanofarad. We have 400 volt, 30 nanohenry, and 20 amp initial condition. What we see here, let's start from here, we see the inductor current going down sort of sinusoidally, starting with 20 amp, of course, going down to 0. We have the voltage of the Snubber going to 430 volt. Okay, this is a one shot, it's not continuous. And then we have the power. This is actually not the power, this is the energy, I'm sorry. This is the current. This is the integral of the current times the voltage of the capacitor, so this is energy. This is not, this is joule, I'm sorry, there is an error here. So this should be energy to Cn, this is joule. So we have about 130 microjoule per turn of instant. So this is the waveform that are expected here in this particular case. So let's now have a look at the parametric run in which I have swept over the capacitance. Okay, the capacitance is swept between 1 nanofarad to 200 nanofarad. Again, the bus voltage 400 volt, leakage inductance 30 nanohenry, initial condition 20 amp. And notice that what we got is the energy is I times VB times square root of LC, and these are constant, and we are sweeping this capacitance. So you see that the energy or the power will be proportional to the square root of the capacitance. This is what is expected. And if I look at the ratio between the energy and the V peak, I get this value or this product, meaning that the larger the capacitance, the larger is this ratio, that is, you have high power and low peak. Okay, so you are paying for the lowering of the peak by extra energy dumped to the capacitor. So let's have a look at the curves here. First of all, here is the current of the leakage inductance. This is for the smallest capacitance. So it's going down very quickly because the frequency is high. The resonant frequency is high when the capacitance is only 1 nanofarad. And then as we increase the capacitor, of course, the quarter of a cycle that we see here, quarter of a period actually, is increasing. Now this is now the peak value of this capacitor. For 1 nanofarad it's very high, and as the capacitance is going up, this maximum is going down. This is now the energy to the snubber capacitor. Again, it's a function of the capacitance. For a small capacitor called capacitance, 1 nanofarad, it's very small, and then it's going up as the capacitance is increased. Now here is a sort of summarizing the results for both the power and the peak value of the capacitance. So this is a plot, this is a performance analysis type plot, which shows in this case, the power as a function of the capacitance of the snubber capacitor, and here is the peak voltage as a function of the snubber capacitance. So we see here that as the capacitance is small, 1 nanofarad, this is the very beginning, we have a high peak voltage, we have low power transfer to the snubber capacitor. But as we increase this capacitance, the peak value is going down, it's approaching the 400 volt, this is 400 volt here, this line here, and the power moved to the snubber capacitor is going up quite a bit, and we have said that this should be something like square root of this value. Now there are two lines here, one is the red one and one is the green one. The red one is the calculation according the approximate calculation, approximate equation that I've developed, and the green one is the actual one. So we see that this approximate equation is sort of overestimating a little bit the power, but all in all, it's a pretty good match between the two, considering the approximation I've made. So these are the typical curves that are expected in this case. So let's have a look now at an actual transistor. This is an IRF or RFP 450 transistor, which I'm simulating. Again, 30 nanohenry, assuming 10 milliohm sort of a parasitic resistance. We have a snubber, which is 30 nanofarad in this case. We have again, this is actually 1 microohm, so basically doing nothing. And here we have the diode. I have not added here the bleeding or the recharging or discharging resistor. This is just one shot. I'm looking at one turn off, and rather than having a lower transistor, I've put here a diode to capture the current once this transistor is off. So this is the bus side and this is the snubber side. So we see again the voltage of the transistor going up, reaching the snubber voltage. We see the current of the leakage inductance, the green one, which is when the transistor is on is 20 amp, and then it going down. And we see here actually the current dumped into the snubber. This red one is the current through the snubber. It's starting here, and then it goes up, and then it's sort of course, following the leakage inductance current. And here we see the power which is dumped into the capacitor, the snubber capacitor. In this case, it's 10 watts. So this is the actual situation. Let me just say that there is some discrepancy between this value and the value that you'd calculate according to what I've shown before, because there are some processes which we have not taken into account, such as the fact that during turn off, some of the energy is actually absorbed by the transistor itself. So not all of the energy is actually passing through the capacitor. Some of it is absorbed here, but this is not a very big part of the energy. So how do we go on actually designing a snubber like this? The best thing is actually to do simulation. Of course, we can do an approximate or a more accurate calculation, but the best thing is to do simulation, and then actually you can trim it in the circuit itself, starting with the capacitor, which is much larger than you need in order to protect the transistor, and then trim it down to the value that will give you the peak voltage that you are satisfied with. So this actually brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.